Ladies and gentlemen, hello and welcome, and let the revolution begin. My name is Eric Kavanagh, and I will be your moderator for this exploratory webcast, this opening salvo in trying to understand what is going on in the world of database. You can see the title of our presentation today is Fit for Purpose, the new database revolution, and it is a revolution. I'm not sure how many of you would agree with this characterization, but I'm not sure that I have seen a faster moving, faster evolving tech industry in quite some time, I suppose with the exception of what the iPad did to the consumer market. But the database market is teeming with action. It's almost hard to believe how much is going on. A lot of it is open source. A lot of the NoSQL stuff is coming from these NoSQL open source projects. Of course, that stands for not only SQL, but there's all kinds of innovation taking place. A lot of in-memory stuff is happening. We're going to be learning about that as time goes by. And I would just point out that this is just the beginning of a year of research. So we're going to try to dig into what's happening, and I'll give you some quick insight into our process. So we outlined a series of webcasts. There will be at least 4 webcasts. This is the exploratory event in which the analysts offer their perspective on what they see happening in the industry. We have also taken very detailed technical briefings from our sponsors, and here's a big thank you to our sponsors. They include Teradata, Sybase, which of course now is an SAP company, MarkLogic, Rainstore, InfoBright, and DataStax. And if you work with a database vendor, there is still time to get involved. Feel free to get in touch with us to be part of this revolution. We'll be posting articles about all of the sponsors at databaserevolution.com. That's a website we have just thrown up to house all this information. And the idea is we're trying to create a center of gravity, a focal point, if you will, for where we can all come and share insights about what is going on. And folks, please believe me, you will play a significant role in this process. We always are very impressed and frankly enlightened by some of the questions that you all ask during these events, certainly during the briefing rooms that we do, and we've now done about 40 of those. And we hope that you will play an active role in that process here as well. So the general webinar structure, what and why, history of the database. We're going to talk about how we got to RDBMS. We're going to talk about relational and post-relational. Then we're going to get into some other stuff as well. So let me make Robin Bloor the presenter. And Robin, I believe you now have the keys to the car. So folks will also be tweeting with a hashtag of DBRev. So if you're on Twitter, by all means, feel free to send us your thoughts and send your questions in at any time. And with that, I hand it over to Mr. Robin Bloor.
Okay, well, thank you for that introduction, Eric. We'll start really at this point. We'll just start going into why there is change. A lot of the content that you're about to experience, I guess, has been kind of put together from discussions between me and Mark Madsen. So this isn't. We're kind of two-handing this, but this isn't necessarily my thoughts or Mark's thoughts. It's kind of an amalgam. Anyway, why is there change? Well, first of all, we have increased data volumes. That makes a difference. Then we have also significant hardware changes taking place. That makes a difference. We have database product innovation. That's been going on for a long time, but it continues. That makes a difference. We have new workloads, and we have different data structures, and that makes a difference. Established database concepts are being challenged. It's very recent, but that makes a difference. And we just like to draw attention to the fact that market forces of themselves can drive change. And I'll just kind of go through a few of these points, but we'll probably be returning to these points as we go through, because these are, if you like, what we believe to be the drivers. So first of all, data volumes. I like to think of this as Moore's Law cubed. Moore's Law suggests CPU power increasing about a factor of 10 every 6 years. And a lot of other hardware technologies kind of stay in step with that. But in actual fact, although there's an awful lot of talk about big data now, we've actually been experiencing a kind of exponential growth in data. In about 1992, we measured databases in terms of megabytes. By 1998, it was gigabytes. By 2004, it's terabytes. 2010, we're now into the petabyte space, and no reason why, as far as I can see, that we won't actually be dealing with exabytes in 2016. So this is a factor of 1,000 every 6 years, roughly speaking. So that's one part. Hardware changes. This isn't everything, but this is actually a big part of the hardware changes. We've picked out the major ones. Moore's law used to proceed by increased miniaturization in line with raising the clock speed of chips. Now it proceeds by adding cores rather than increasing the clock speed. So that kind of makes a difference to the way that you want to run processes on hardware, and it makes a difference to the database. Computer grids using commodity servers are now relatively inexpensive. You could always have put a grid together. It would have cost you a fortune. Now you can do it for relatively low amounts of dollars. So computer grids actually have become resource spaces in which you can throw databases, and that didn't used to be the case. Parallelism is now on the rise. That's primarily because of multi-coring chips, but it's also because of computer grids. And it will eventually become the normal mode of processing, but it wasn't the normal mode of processing. Pretty much the only software that used parallelism much was databases, and they tended to parallelize themselves across clusters and nothing bigger than that. Memory is now about 1 million times faster than disk, and that means that random reads have become very expensive in respect of latency. So for a lot of applications where you might have used random reads, we don't do that anymore. We tend to read serially from disk. And we now have solid-state disks that are augmenting and may eventually replace spinning disk. The graph of trends suggests that probably by 2016, 2017, because of the way things go in terms of the cost of manufacture when a particular item gets to be more and more used, that may be the point at which solid-state disk crosses the line of spinning disk, and we start to see spinning disk disappear. But there's no guarantees. It's just likely. This is a graph. Actually, we seem to have a kind of graphical error here, so I'll try and explain the lines as I go. But basically, if you actually look at data against time, then we not only have the increase in the volume of data, but we actually are moving from transactional data to what tends to be query-only data. And as time goes by, less and less of the data that we're actually working against is actually active in the process of being changed. We are looking at historical data, and in the end, the vast majority of data becomes historical. Those curves were we were only supposed to see part of them, but they are application performance with time starts to deteriorate, and cost in dollars and the pain of getting what you want increases over time. On to the next slide. This is the market forces equation. We've seen this. This isn't a database-only thing. This happens to pretty much every area of technology when you get some new technology introduced. First of all, a new set of products appears, and they include some fundamental innovations. So they are, in effect, challenging existing products. A few of them are sufficiently popular that they manage to establish themselves. The force of fashion and the force of marketing dollars drives greater and greater adoption because the companies producing this technology invest more and more in getting their message out, and people see it as a new and exciting thing. These things normally come with product defects, but in time, because the revenue goes up, the product defects begin to disappear. They get addressed. They don't all disappear, but a lot of the ones that might have made you feel reservations about using a product, sometimes they just vanish. And then, quite possibly, they eventually challenge the dominant product. And we've seen this with the iPad. I mean, in the consumer market, it's much more obvious and it's much faster. But the iPad is now eating into some areas of laptop usage. In the same way, we expect some of the new breed of databases to become established, and maybe they will challenge the existing incumbents. We see it anyway as possible because this is a repeating theme in the history of technology. Okay, so section 1, how did we get here? I'm doing the period from pre-relational to relational, and after I've hit relational, I'll be handing off to Mark, who's going to do relational and post-relation. This is really what we had in the prior technology regime, so in a sense it's where we came from. It involves what we traded away, why we traded it away, and to some extent, was that a good idea? So let's start with the dawn of database. There's probably not many of the people listening here to this broadcast that were actually in the computer business at the dawn of database. I was kind of only just in there. But it was actually quite exciting. I mean, first of all, it needs to be understood that database was once just a mainframe thing, and pretty much all of the early databases were running on IBM mainframe. And there was a huge variety of them. And they brought a number of things with them. First of all, they established the idea of a schema. Prior to the existence of database, data was held in file systems. The data was defined in the program. The programmer, therefore, had a reference to the metadata of the data, but that reference was specific. It wasn't widely available. It wasn't necessarily consistent because there was nothing to enforce its consistency. And so one of the things that database introduced was a schema, and the schema defines the logical structure of the data. It's the business of the database itself to determine what the physical structure actually is when it puts it away on disk. And that's the way the database came out. The reason there was a lot of excitement in early database was that the existence of a schema made it possible for not just third-generation languages, but fourth-generation languages, which evolved fairly swiftly, to use this schema as a place of data definition. And because they did that, you could have many, many applications running against the same database. And that's where we came from. That's why it was done. And in the early days, there was an incredible amount of optimism, even to the extent of believing that maybe a single database would be all that an organization required in order to run all its applications. Well, that didn't happen. The second thing was that in the era of codicil, the pre-relational era, they defined what are called the ACID properties, which are atomicity, consistency, isolation, and durability. And basically, these all revolve around the transactional view of data, and not just the transactional view of data, but transactions that add data, delete data, and change values within data. And the rules were distinct, and you weren't really, unless you obeyed the ACID properties, you couldn't really be considered to be a bona fide database. So the transactions themselves must be atomic. In other words, a transaction starts, it hits the database, and then it's over. The database puts it away. They had to be consistent, so a database had to ensure that one transaction did not interfere with another transaction in terms of the way the data looked after all transactions had completed. They had to run in isolation, so they weren't dependent upon each other, and durability had to be there. In other words, a completed transaction caused permanent change, and that change was, I suppose, set in concrete. And those, I think, were the two fundamental things that happened with the early codicil databases. They didn't agree on how they arranged data. Some of them were very good at hierarchical. Some of them looked a bit relational. I think Datacom DB looked to me a little bit relational in the way that it organized its data. But each of them had different physical structures, but they also had different logical structures, and there was no easy way to take an application that ran against one specific database and move it to another. In actual fact, that was probably very hard to the extent of being undoable. That was stuff that you didn't do. So that's where we started from. At that point in time, now I put this slide up so that we have all of them, but at that point in time, the performance bottlenecks that everybody worried about were, first of all, you could run out of CPU muscle, and that would cause delays to transactions and disturbances to whole workloads, if there were batch workloads. You could saturate the memory resource that was available, and that's a different bottleneck. You could saturate the disk I/O channels, in terms of how much information was passing into memory from disk. You could create a bottleneck by locking amounts of data, which meant that other processes simply couldn't get at that data until the lock was released. We also got, and we continue to get, the idea of network saturation. You can think of it in terms of networks in a grid, because the connection between the various nodes of the grid can become saturated, but you can also think of it in terms of bus saturation or saturation of the interconnects in a cluster. So there's different kinds of networks, but any one of them in one way or another can become saturated with traffic, and they get more saturated the greater volume of data that they have to carry. And finally, we have the bottleneck of parallelism. Given that we are actually doing a lot of different things in parallel, then you can inefficiently balance the load and you lose the advantage of parallelism. So those are the bottlenecks. And they apply to the old databases, and they apply to everything that's come since. And it's one of the, if you like, it's one of the dimensions of database, because at the end of the day, database is either about individual transaction performance or query performance, or it's about the whole workload performance if nobody's waiting on it until the workload's over. But you actually have to care about performance with database. One of the things that it's supposed to do is to make that something that you don't worry about. Okay. Then came relational. And I remember the advent of relational really well. I remember, first of all, that people started talking about the normalization of data, which was a technique to arrive at a design which was supposedly correct. It's kind of correct in inverted commas. If you take any given area of data and you apply the rules of normalization, most people will end up with the same model, so it works well that way. In actual fact, normalization is a technique that's been taken out of mathematics, ring theory of mathematics, where it's much more precise. Ring theory doesn't really apply to data, so it's a kind of borrowed idea. And you can join tables together along a common column. And you can also, SQL provides quite a lot of additional capability if you go down into the depths of it. Yes, you can qualify all of these SQL operations with order by, with group by, and so on and so forth. SQL imposes some limitations on the logical model of data, and it's worth kind of opening this up. in the sense of it is not a perfect algebraic representation of how data can be. Very specifically, it gets itself into trouble with hierarchies. If you get the traditional objection, I suppose, to SQL, because it was certainly an objection in the early 90s when people were discussing its capabilities, is that it doesn't have any recursion in it, and because of that, it can't do a bill of materials off a single table. So you end up having to design around. If you're going to process data like that, then you actually have to design around the structure of the relational database rather than have it take care of it for you. It can also create a barrier between the users and the data, and I'll kind of touch on that in a couple of slides. But it's also worth noting that even though there are drawbacks to SQL, what it actually did do was that it provided one common language that allowed you to be able to get at any database that supported SQL. So the previous objection to the codicil database is that you couldn't really lift an application from one and drop it onto another. With SQL, well, you probably don't want to do that, but it actually becomes feasible for you to do that. So there's a level of interoperability that really didn't happen before, and if nothing else, it should be applauded for that. Now, quoting from the Bible of relational data, relational database, a data set is an unordered collection of unique, non-duplicated items, which is fine, except it's a reality that data is naturally ordered by time if it's not ordered by anything else. Events are ordered by time, and therefore changes to any entity in the database will be ordered by time. And there is an audit trail of changes if you actually have access to the time of every change that occurred within a database. The actual reality is that having an inherent physical order to data can save a lot of processing cycles for some areas of application. And there are some products out there that actually do intentionally put an order on the data. But the relational dogma, if you like, was that it's actually an unordered collection. And that, in my opinion, turns out to have been not so helpful because I think that a number of problems caused by a lack of order were ignored for a long time. And that's particularly the case when you look at time series applications. We've only kind of got into time series applications in the past 10 years, so it wasn't really a big blocker. But certainly if you're actually doing an awful lot of work with time series of data, then you actually really need to care about the ordering of data. Then we have the RDBMS Optimizer. It wasn't that the codicil databases didn't try and optimize access for data, but the relational database took a very, very specific conceptual approach, which was this. The database can know more about how to access data than any programmer can. It knows where it put the data, so it will know where it can get it from as long as it keeps the right information about that. Well, when relational database started, this simply wasn't true. There wasn't anything in terms of sophisticated optimization of access to data at all, and pretty much you were kind of trying to guess the way that the engine would do things. But then, and I think this was between the early 90s and the late 90s, it became true. The optimizers just got better and better, and they managed to be able to execute their promise, which was much, much better than a programmer trying to get at the data because he sort of knew how it might be read. So it took that activity away from the programmer. But optimizers have problems. So it isn't actually always true. It's only true for probably the major workloads that they're good at, that they actually optimize the access to data. And of course, optimization is pretty much, 60% of what a relational database is about, because it's trying to save you all of that work. But there's this other problem. the data in the database can be regarded as persistent data, and it's persistent because you wanted it to persist. But the database only optimizes for access to the persistent data. So if you start to do something kind of interactive with a database, and you throw a query at it and you get a result set back, and you mess about with that result set, maybe on the desktop or something, and you think, well, I'd actually like to join that to something else in the database. Well, in actual fact, the data that you've created and messed with is no longer in the control of the database. You can't do that. So there's an issue here, and the issue is that SQL can create a barrier between you and the data. And you might want to be doing statistical things, an awful lot of analytical things. You can put them in the database, but if you put them in the database, they only apply to the persistent data. You can only use them on a persistent data. And if you don't put them in the database and you leave them in some program somewhere, then you've lost some of the optimization that the database could be doing for you. So it's an issue. It's not a completely defeating issue, but it's an issue where some products claim to have made a really big difference. Okay, I'm now going to hand on to Mark, who's going to tell you more about relational, and he's going to also deal with the post-relational phase of database history.
Yes, and I've made you the presenter, Mark, so you should be able to just push the slides yourself.
Great, thank you. So, I'm just going to talk sort of quickly through some things. I mean, the high points of that history being that pre-relational was really, in the fundamental models, hierarchical and network databases. And one of the problems is that, you know, with relational, you have relational algebra, which allows you to construct things in a declarative fashion. And that declarative fashion relieved a lot of burden. And that idea of SQL as the API rather than SQL necessarily as a programming language, as people always think of it, was an important thing. And that changed a lot because it relieved the programmer of having to do a lot of things they used to have to do. And then with relational, we ended up where we are today with this model, but in some ways it was possibly a premature implementation, or the fact that relational databases in the universal database vendors, the big SMP traditional vendors that 99% of us use today, they're really useful, but they impose some limitations that create challenges. And one of the big ones happens to be horizontal scalability. Years ago, up through fairly recently, like the past decade, the way that you got scalability in these kind of transaction processing applications, not query applications, was by using a transaction monitor, an application server, something that would multiplex lots of requests into fewer connections to the database, punt them off to the database, which would execute the transactions. And the big shift came with web architectures and the need to have horizontal scalability, but not have to sacrifice availability. And there are still concurrency limit problems to a single machine architecture, and unless you can find ways to relax dependencies between these things so they can be parallelized, it becomes very difficult. And you combine that with the other things that have happened, namely the internet happened, and the constant advancement in hardware where we had compute bandwidth, disk bandwidth, network bandwidth all increasing. We could do things we couldn't do before. Those early systems were built under heavy resource constraints and in terms of data volumes, trivial by today's standards. And that kind of got us, you know, the SMP parallel databases, which is where I learned databases. I learned them going from monoprocessor systems or uniprocessor systems to symmetric multiprocessing and non-uniform memory architecture systems. And that was a big transition with a lot of learning, and that we've spent 20 years learning. And now we're at this new era. And one of the interesting things is that where we are today is closing a loop with the past. a lot of these new databases, these NoSQL databases, which can be either NoSQL or they can be not only SQL. You know, they'll have a SQL-like or fully SQL standards compliant language attached to the database, but they'll also have other mechanisms. But under the hood, they're non-relational. They are faking relational through the API, or they are doing some things that are hierarchical, that are network-oriented, that are graph-oriented. And those are things that, well, they're just not really there in SQL, and so you have to kind of work at it to make some of those things happen. And that happens to be the way a lot of code gets written. Now, if you really look at where today's NoSQL architectures have their theoretic roots, it is in those pre-relational technologies of the 60s and 70s and even into the 80s. But if you look at how the web architecture evolved, we went from a stateless web server where you could have multiple, and then we realized that we could actually start to break apart applications if we were careful about how we partition things. And so we ended up with a load balanceable, distributable over HTTP web server architecture, app server architecture, but things still all ended up in a single database in the back end. And the really big websites had to figure out ways around that, and so we ended up with things like sharded MySQL, which, if you're not familiar with that, is just, it's a way of vertically partitioning chunks of data so that they are isolated to specific machines, so that if you lose a machine, you lose a portion of data, but the overall system still remains up and functional. And when that node gets restored, that data comes back. And then, of course, you can play tricks with replication, n-way replication, and so forth, and cleverness about redirecting to where the data is stored by storing master indexes. You can build a system that is resilient to failure, but also remains available even if a node takes a hit. You might have to roll some transactions back because we are losing some levels of ACID compliance. But that was really not an optimal architecture because it still had type limitations. It had constraints put on it by a relational model for databases that ran on a single server. And so where we see the NoSQL databases step in was kind of introducing a different way of thinking about database, relaxing ACID constraints, whether they be durability or consistency or partial availability or data latency, different ways of changing what we consider a database. And one of the big things also happened to be taking SQL out of the equation because we can make things a lot faster and simpler. So what we've done is we've, in a way, rediscovered a lot of the past, built hierarchical data stores, network data stores, object data stores, but with twists on the past, with really incredible resources available, and parallelization, which was really not a consideration, much more modern and up-to-date languages that are much further removed, including DSLs, which give us even more capabilities, and then parallel capable languages are really the next frontier. And so we now have a revisiting of old arguments, object versus relational, hierarchical versus relational, SQL sucks, SQL doesn't suck, all that kind of stuff is happening all over again. But we're also challenging assumptions, which Robin outlined very, very concisely. Pre-relational databases assumed two things, schema and ACID. You typically didn't have schema-free or ACID-less databases. The modern implementations of similar theoretic concepts actually relax those constraints and challenge those assumptions. The whole thing about eventually consistent models, where it might take 10 seconds before a query returns a consistent set of data, or hopefully less than a second, which is where most people kind of target eventual consistency. But that means that you have more freedom to scale horizontally, which is what you need if you're going to have 200,000 simultaneous connections. And that's about the biggest system that I have personally worked on. Now, when I was working earlier in my career, say 15 years ago, the biggest relational database with simultaneous user queries happening that I worked on was about 7,000, and that was actually one of the largest in the world in a conventional relational database. And so we've gone orders of magnitude beyond that thing. Now, what we've got then, for some reason it's not advancing. Eric, can you just advance the slides for me?
Sure thing.
I'll wait for the slide to advance before I talk. So, you know, what we have then is lots of product innovation. Many of these things existed prior to relational, and some of them existed because of new needs. You know, document stores, and we're talking about documents like your loan for your house or your car loan. Doc stores are really a type of content store with special needs, and content stores evolved to meet website needs, you know, serving images, but not just serving them, but also maintaining metadata histories and versioning and all these variations on object stores. XML databases are interesting because they are, in essence, hierarchical data stores, but they're also blended with document stores in terms of how you might think of them. There's all kinds of different things. We forked off analytic databases because query workloads for complex query are fundamentally different than transaction processing. And in fact, you don't have as much to worry about with consistency because you're typically not updating data in an analytic data store. But as we get to things where you need data on a more constant basis and refresh data, you start to reintroduce a workload of transaction processing and query and reintroduce locking and consistency and availability issues all over again. And that becomes very hard. And so what you'll find in the market is that most analytic databases are great for query, bulk query, business intelligence, data mining workloads where they're streaming off data, but they're not very good when you start trying to insert and update rows in that database simultaneously, and the best databases cut their teeth on the ability to handle mixed workload in these things at scale on a shared nothing architecture. And then we get, you know, further afield into graph stores, which are really, really great for navigating complex graph structures. Why do we need graph databases and triple stores and these other things? Well, we need them for a number of different reasons. Now, if we kind of roll that back to the relational model, one of the big things that's come to the forefront recently, I'd say recently, it's really the past decade, has been column stores. And there's a lot of different ways of doing column stores. We won't go into that, but they are relational databases. They have schema, they use SQL, they're just like a database, except that under the hood, the engine stores data differently. And they can do this because we now have the memory and the CPU that we couldn't afford before to address what they can do. They take a lot of extra effort because you have to burst rows apart or stitch rows back together because they're stored column-wise instead of row-wise. And that creates a lot of extra work, and then there's compression and a bunch of other things. But for a traditional BI and query workload, not so much a transactional workload, they can be orders of magnitude faster, especially when you have things like large rows with lots of measurements on them, of which you only ever need a few at a time because you are reducing I/O via not querying and reading off of disk those columns, but also the compression of a column is much more efficient than the compression of a row because the data is in one value domain. It's all integers. It's probably bounded at some level, and it's all one type, and specialized compression algorithms can be used on different types. And so you can get 10, 20, 30 to 1 compression ratios instead of a 2 or 5 to 1 compression ratio on a row store. Now, one thing, column family, if you're working in the NoSQL world, is not the same as column store in the relational world. These are two completely different things. A column family is much more like, well, for the most part, a doc store or an object store, usually built on the back of key value or distributed hash table models or something kind of funky like that. So, you know, that's where we get into these things with websites and big data centers, and we have to start to carve things up a little bit. Big data and so forth and NoSQL are used as interchangeable, really hideous terms. And the problem with these terms is that they assume, you know, big data means one thing and NoSQL means one thing. And NoSQL is a great way for a lot of people, projects, vendors to sidle up to the bar and in a unified voice trash relational, and a lot of the criticisms are you know, valid criticisms. But the flip side of this is that when you have this impression that all NoSQL databases are, you know, better or different than relational, and these things are all labeled NoSQL, they're interchangeable. Well, they're not interchangeable. You can't necessarily take a Cassandra and swap it with a Couch and get the same results. You can't take Couch and Mongo, or Mongo and Dynamo, or Bigtable, and change these things around and expect the same performance characteristics, application interfacing characteristics, behaviors of transaction scale, concurrency, data scale, query complexity, and on, all those different factors. And so what you have to understand is the underlying technology of these things. What are they? How do they work? And there's only a handful of fundamental models. And those fundamental models have various restrictions and capabilities that go with them. And that's the key to understanding how and where they fit. And so, you know, when you take the early pioneers in the sort of big data side, where we're talking about analyzing and crunching that data, which is really a business intelligence query or analytic workload, and segregating that off, you have one set of technologies. And you could lump things like Hadoop and Hive into that bucket as alternative ways to do these things. The other side of it is transaction processing. And I would say that 90% of the project and vendor offerings in the NoSQL space are actually targeting application work more so than they are targeting analytic and query workloads, because those workloads benefit from certain things which are inherently relational in nature. If you take some of these types of databases, they have very specific things that they need. I'll get into that in a moment. And so really, the modern day database revolution got jump-started probably around 2004 as this stuff started to come into actual practical usage, and it's just rapidly accelerated since. In much the same way that shared nothing MPP-style databases that were relational got jump-started about 7 or 8 years ago, you know, when we saw Netezza launch, and when we saw companies like Vertica and Parexel and, you know, vendors that have all been absorbed and disappeared since then, you know, Astra, Greenplum, which are now Teradata and EMC respectively, or Data Allegro, which is now Microsoft's parallel data warehouse. Those are horizontally scalable relational databases that maintain, for the most part, ACID compliance, schema, SQL as the API. So you do have horizontally scalable SQL databases, and this is one of the things that a lot of people working in the NoSQL world don't realize, or just assume that, say, a Cognitio or an Aster is a non-relational database, or a column store like a Sybase IQ is a non-relational database. So those are all in that relational camp, but these new things that are truly non-relational are different. Now, I've started to track databases, and the list of ones that I can validate as still being sold or projects still being contributed to, which changes on a daily basis, is up over, well, it's, as I've been able to match so far, about 150. This is just about 50 of them right here. And they span all sorts of ranges because people are pushing product boundaries now. They're saying, well, what if we mix content indexes in with the data store and blend them, which is something that you could do in Endeca or Sand, and you could have your SQL queries and your content indexes simultaneously, which is a pretty novel thing, or using funky things underneath. And so you could use these indexes as a storage mechanism. And so there's interesting products like MarkLogic and RainStore, which store data in tree structures and specialized content indexes and other things. And they allow you to do things that a conventional data flow engine a la a SQL relational database maybe can't do. And so we've got blendings, we've got purpose-built for a specific thing, like, say, a couch or a Mongo. We've got universal databases trying to be everything, right? A Greenplum or an Aster marrying MapReduce to the SQL database. And then, you know, things that we aren't really going to talk about here, like streaming databases. What if things flow over the network and never actually land, or they are persisted elsewhere? And so you're really talking about a standing query and moving data instead of a query that sits there and you flow the data through it, which is what relational databases do. In fact, there was a really cool project called Flume-based that sat on top of Flume, which you're from the NoSQL world, you know what Flume is, that really deals with data streams, but allows you to project SQL on top of those streams. Unfortunately, that project is recently defunct, the only open source one that I was aware of that could do that. So on to discussion topics, as we're now in this sort of world where we've got some of everything, and what some of the assumption changes are. And this is where Rob and I kind of open it up to some questions from the audience, but also some of our pontifications, because we don't have a lot of set agenda at this point as we try to tease apart how you figure out which technology is best for what purpose, and then within that technology, what are the factors that help you to evaluate it? How do you differentiate between 5 different key value stores to support a horizontally scalable website running in the Amazon cloud? And how do you do that same thing under a relational model with a horizontally scalable database or some other model? So that's where we come into the post-relational changes in assumptions. And I would characterize those at the moment as schema optional. You don't really have to have a schema anymore if you don't want to. But the question then becomes, what do you do and how do you access the data if you don't have a schema? Because you now have to write a program to consume it. SQL is optional. Actual relational algebra underneath is optional. ACID compliance is optional. And so these are the kind of assumptions that are changing things around. And I think this is where stuff gets really interesting, and the difficulties that programmers face in constructing applications around a relational database when using modern programming languages and development environments is something that the database community has been ignoring for far too long. And the flip side is that because of the difficulty of doing that, programmers have junked the relational model and said, this stuff is crap because MySQL is crap, or this stuff is crap because, and then there are mismatches with the models. And so if you talk to relational database vendors and they say, well, we can do computation over data in parallel, but the only way to do that is to write C++ code executing in the address space of the database kernel using a custom API for user-defined types and user-defined functions, you've just restricted the number of developers in an enterprise capable of doing that to about 12. So, you know, that's one of the problems we've got there. Robin, did you want to comment at all about some of the assumptions or go into some more detail on that?
Well, it's one of the things that I just think has been if you like, a trend over the years is that relational databases started out pure and then they started getting dirty in one way or another. And they started to, if you like, add stuff to get over the problems that were created by strict adherence to the model. So some of this, what you can do in the database, was the relational vendors trying to address the fact that initially you couldn't do anything in the database apart from ensure referential integrity and make cascade deletes happen and things like that. All of a sudden, it actually is a really bad idea not to be able to stick some functionality straight into the database. And that's certainly the case with analytical database. But of course, as soon as you put the programmers in charge, the metadata of the data vanishes out of view and finds itself completely embedded in a program. And you've got no specific scheme for surfacing that metadata. It's not so much where the metadata is actually being held, it's the fact that it's not there anymore for general access. We've got tools now that can make life an awful lot easier, like the invention of XML I thought was a really good leap forward in the database space, because you could throw data around and you could throw its metadata with you. You weren't static anymore. So I thought that was kind of a good thing. But I kind of get nervous about some of this very program-specific stuff that's happening in the NoSQL databases. I mean, don't you?
Yeah, and we've got a good question here about workload, and I know this is going to be a real key focus of the research, is understanding the different kinds of workloads that are necessary and suggesting which kinds of technologies to use for them. So I just dug up the slide from Deep in the Deck. It's slide number 39 for those of you who are following at home. But do you guys want to get into workload now, or do you want to save that for a little bit later?
No, it's fine to talk about that now. You know, one of the interesting things about the assumptions was that for a long time we've operated under an assumption that the database is universal. You can query from it, you can execute transactions against it, but early on we realized, first because of resource bottlenecks and query constraints and performance difficulties, that maybe executing over a transactional data model wasn't the best way to go. And then we still built a database that theoretically could handle both workloads, but as the workloads have continued to diverge, we've started to get into what Robin likes to call the horses for courses approach, where, you know, if it's raining, certain horses are going to win, and if it's dry, other horses are going to win. And I think we'll probably touch on some of the workload details a little bit later.
And we've got a bunch of good questions in the Q&A, so if you guys want to take a look at that Q&A, we can start digging into some of these. I'll just start throwing them out, and we can talk about this stuff. So one of the attendees writes, SQL provided the ability to abstract data from applications and then provided investment protection for applications, basically. Are some developers losing sight of this? Shouldn't CIOs be concerned when developers throw this idea out the window?
Well, that's contextual, isn't it? Because it depends why you threw it out of the window and when. You know, it's like in my dream of a perfect world, there's some kind of amorphous pool of data that's sitting there under the data center, or actually under the data center and the cloud itself. And when you want to do a certain kind of thing to it, it surfaces. In an engine that you can do that kind of workload to, and we're so far away from that it's almost ridiculous. But in the world of ideals, that's what I would like. The thing that I think is unfortunate is that it's been the big data problems that have actually given rise to products that start violating these things. And it's absolutely the case that one of the things that's violated is your view of the data. You know, and it wouldn't be so bad if these were just kind of little data marts that you pulled out of a big, well-organized, well-managed pool of data, and you just ran those stuff against them, because you could get, you know, back to that data. But no, that's not what's happening. What's happening is very, very big heaps of data and data no longer visible. I think you have to be careful, but you know, if that's the only engine that's going to do the workload that you need to do, then that's the way you're going to go, because, you know, needs must when the devil drives.
Here's actually a really good question. Oh, go ahead, Mark.
I was going to suggest, you know, when you look at types of workloads, you know, as we dig into kind of a sort of research report and trying to characterize some of this to make the job of figuring out what to use when, and also to some extent, what technologies do you make long-term plans on? Because we're in a period of product and project, in the case of open source, market, where many different things have the possibility to win out. And the incumbents, while seemingly not threatened, are seemingly not threatened in the same way that all the mini-computer vendors were not threatened in the 80s and 90s, or the mainframe was not threatened. And so we've tried to segregate out workloads because workload is actually key to figuring out technology matching to a project in the short term. And then to some extent, the technology analysis is separate and distinct from that for which bets, which horses you're going to bet on over the long term. And this slide just shows that the workloads that we've been considering, and that there's a big difference between a conventional transaction processing workload and object persistence, or what we call OLTP light, where you're doing things like creating a profile on a website. You're not dealing with ATM machines and debiting and crediting bank accounts. You're doing stuff where maybe a little inconsistency over time or a little loss of durability isn't such a big deal. And query workloads are either write biased or read biased. The problem is that most of them are actually a mix of the two, because you've still got to get data into systems you're trying to get data out of.
And there's another couple questions I just sent through the chat to the panelists, so if you guys want to take a look at that. And while you look at those, I've had several people asking about solid-state drives, and of course we've talked about, at least briefly, some of the impact of in-memory database technology, and I guess that's one of the areas where schema is optional, because memory is, what, 1,000 times faster than disk or more. So how big an impact does in-memory have on changing the landscape? And, we took a briefing for the Air Force from SAP HANA, and it looks very interesting. We're still trying to get a more detailed briefing on what's going on there, but that's obviously an in-memory appliance. And there are lots of these vendors that are coming out with in-memory technology to really supercharge analytics, I guess. But I guess, Robin or Mark, how big a deal is in-memory, and how big a deal is all these solid-state drives?
Well, I mean, first of all, the solid-state drives are a big deal in the sense that they're faster. So, the first thing that is obviously going to happen is when the price gets more and more even, then the solid states are going to knock out the spinning disk. I mean, it's going to happen. So they're significant in that way, and that will actually make a difference to latencies from disk into memory. But I find the in-memory database question a really interesting one, because there's another assumption here. One of the assumptions that database was making all the way through the decades was that that's where you put persistent data, and the data that you don't want to persist just kind of vanishes into thin air. Well, once you've got an in-memory database, the question is, what exactly are you going to use that for? Are you going to use that only for persistent data? I mean, it's going to be a very good cupboard to put stuff in that you want to get out fast, even if you only want it to persist for a couple of hours or to share with somebody else. So I think that's a potential nuance to add to the in-memory stuff. If memory gets cheap enough, then disk disappears, that's fine. But, that's not just the issue. The issue is, what do you want to persist? And, one of the things that's actually happening right now with all of these big data heaps is that we are making data persist that we didn't make persist before because we couldn't afford to.
I think that's a great point. We are saving things where the conventional solution to performance was to delete data that was more than 3 years old. In fact, I have a DBA friend who constantly argues for that. The other side of it, too, is that there's a lot of write-once data, and write-once workloads that are different. Transactions sort of assume a lifetime of a transaction. You buy something, you might return it, there might be adjustments. And so there's an update period to this stuff, as well as simply recording it for analysis. But log structure data, you know, the clicks in a website or call detail records or other things that exist in a time series, they have a different set of characteristics. You only ever need to append that stuff because it doesn't get updated. It can't be updated because the sources don't permit updates. And that creates huge volumes of data, but it's data either irrespective of or about things like transactions. And so the data volumes magnify. But the thing is that the data in itself, an individual field in a transaction, like a row from an order, there's some useful data. You know, there's dollar values and product IDs and things that you can analyze in that, or even just look at in an individual. An individual click from a web session is meaningless. What's important is the derived patterns that come out of the set of measurements of the time series itself, or across the collection, you know, being like a collection of web sessions. If you take enough of them and throw them in, you begin to see common paths through a website. Or if we take Twitter, I've done a bunch of Twitter analysis and social network analysis. All these tweets and retweets and at replies and things like that, over the totality of the collection, they surface networks, implicit networks, not explicit follower relationship networks, but implicit networks of community of discussion and so forth. And those patterns are inherent in that giant collection of data, but you only see the pattern by looking at 100% of that data. And then the question is, well, I have just flowed a bunch of read-only or write-once read-only data into a giant data store, but then I derive these implicit patterns from the data collection. Where do I put those things? Because you now have second-order data and patterns coming out of first-order measurements. And so that's maybe the thing that you schematize into a graph database or a relational database. And then the question is, do I really need Oracle or DB2 to store all of that earlier stuff? Why don't I just stick it in Hadoop, run Hive against it if I need to pull out a subset, or use some MapReduce, you know, job to crunch the numbers, give me the implicit patterns and store those patterns, which I would call the high-value data that you might take action on.
Yeah, and that really gives some good insights on how to re-evaluate the entire architecture of your database strategy, right?
Well, yes, it has an impact.
Seems to me, here's a really good observation that one of the attendees writes, and maybe you guys could comment on it. The comment says, fit for purpose cannot mean an enterprise must institutionalize a large portfolio of database technologies. What we need is a minimal spanning set that may sub-optimize on a design point or two, but keeps the TCO for the enterprise's DB tech investment down. I think that makes a lot of sense.
Right. And, you know, you could take Amazon's Dynamo, which, you know, it's a NoSQL database, so you can't do a lot of things with it. But I was really surprised at the headline that nobody's written yet for the Dynamo DB update announcement from Amazon wasn't the cost per terabyte metric that everybody's been throwing out there, because, you know, people have been making sort of single vendor database decisions. I think minimal spanning set is great, but then you throw in metrics like cost per terabyte, at least in the analytics world, which, you know, $100,000 per terabyte, $50,000 per terabyte, to Amazon Dynamo cost of $1,000 per terabyte, asterisk included. And, you know, the portfolio, I think the portfolio choice gets interesting because we can't really assume that there is only one database, because there are things which we can't do in the current technology. So we need that minimal set of a NoSQL store that supports the website and the kinds of rapidly changing schema and things that happen there. The analytic database for the analysis of large sets of data and the relating of it, because let's face it, you can't easily relate data in a Cassandra or a Mongo. You have to use something else to do that. And, you know, that would be the query by attribute sort of questions as opposed to other things. And so you have a few different needs which are isolated kind of by workloads or application types. And that's the really hard to determine set right now. And something that I would throw out there that we have not talked about is what the impact of cloud is. Because, you know, we're talking virtualized data center. But virtualized data center means virtualized disks, and databases have been optimized very close to hardware. Well, what happens when you run that thing in Amazon? What happens when you run it in shared nothing mode in Amazon? What happens when you want some level of consistency, or you don't care about consistency? And what are the architectural matches between, say, a Teradata and an Amazon cloud, a Vertica and an Amazon cloud, and a Dynamo and an Amazon cloud? And, you know, that gets into load scaling and dynamic provisioning and elasticity, which, you know, you can have the most elastic hardware in the world and environment in the world, but if you have to take the database down every time you add a node, it's not very elastic, is it?
We've got a number of other... Oh, go ahead, Robin.
Well, it's just that I wanted to kind of amplify a point that Mark brought up earlier, which I just think is very important, is that a lot of this big data stuff is actually event data. It's a very simple event. It traps everything to do with the event. And people build that up into derived data because the event data itself isn't the whole enchilada, if you like. So they build that up. So this creates, for me, you know, this creates an increasing realization that we are going to event-based architectures. And therefore, at this point in time, we may see further innovation that maybe we can't even surface in these discussions, simply because once you start to rethink the whole of data, we aren't transactional anymore. We're event data and transactional data now. And when we have that, really what is, you know, really how should we be thinking about data, and how does that make a difference to, let's say, a master data management project that's trying to, you know, at the highest level, resolve the actual meaning of the data that we've got out there? And I don't think these questions are answered. I think at the moment they're just questions.
Well, we're hearing a lot about hot data and cold data. I've heard several vendors now, including Teradata, including some others that I've been tracking, talk about this sort of liquid data, meaning they'll find the hot data, move it to in memory, for example, or take the cold data and move it down to disk. Is that a common trend that you guys see happening?
Well, I would say it was always happening because you always had caching, and it's a form of caching. It's just that now it's being done really sophisticated, in much, much more sophisticated way than caching was used before.
Or caching and ILM and, you know, movement. I mean, you know, how we used to move stuff on and off of tape in the past. But the, you know, the interesting thing on the technology front is how storage class memories are going to change that and blur that line even further. You know, storage class memories sit sort of in a latency pool in between memory and things like solid state.
And what about, we've got a couple questions about semantics. Can you guys talk about semantics? I know, Robin, this is something you've talked about many times before, and I think you've got a hard stop coming up, but Mark and I can stay on for a few more minutes. But can you talk about the role of semantics in helping to reconcile some of these disparate database technologies?
I don't know whether semantics will help in that. Well, at this point in time, I don't think. I mean, one of the things is that while we champion the idea of a schema, the schema is not a semantic description of the data. It just isn't. By putting data in a database and representing that database in terms of the kind of information that is in a schema, you've actually lost semantics. And one of the things that's happening, and one of the things that there's some excitement about, is this whole idea of triple store, because triple store is based upon the fundamental semantic atom. It's a triple, it's a subject, object, verb kind of triple. You can trap meaning in that, but there is nothing that I've seen that spans the enthusiasm of triple store with the technologies that are actually being deployed now, because as far as I'm aware, there's nobody out there that's really doing anything with triple store in anger. So I think that, you know, this is a space yet to be filled. But ultimately, the only way that we will resolve this kind of confusion in terms of data is through having semantics that can actually be applied to it, because then we will have a level of certainty about what we're talking about when we retrieve any data from anywhere.
Mm-hmm. And you know, there's another good question here. It's actually more of a comment, and I'd like to hear you all comment on this. One of the attendees notes that major relational database vendors apparently did not see or did not handle in a timely manner this whole big data movement, and that's one reason why we see all of these other projects cropping everywhere. Of course, Oracle has their new Berkeley DB version that they've just been touting since, I think, October of this past year, so that's pretty new. And, of course, Teradata went out and bought Astrodata. So you've seen the large sort of powerhouse vendors go out and pick up what they feel are the appropriate NoSQL vendors. But can either of you offer some context on how this all came about? And is it just because of big data, because of all this machine-generated data and, you know, Twitter street feeds and social media and all these things? It's just sort of a confluence, or how did we get to the point where it's just exploding these days?
Complacency?
I think that's right. I would go in complete agreement with Mark. It's like they'd been watching the graphs, and the graphs were going up, you know, at the rate we suggested at the beginning. You know, they knew their engines were going to blow out at a certain point in time. So I can't think of any other word than complacency. Do you want to elaborate on that, Mark?
Well, it just seems like, you know, it's like any technology vendor. You get so enamored of the status quo, and everybody's using it. I mean, truly 99+% of the market is, you know, I'm guessing, is relational. But, you know, that 1% can change things very quickly. And you look at how much money Oracle and IBM and Microsoft stood to make in databases behind websites. And then along came MySQL and basically swept that, not only swept the revenue off the table, but devalued the revenue to the point where it wasn't a market really worth addressing. And, you know, that kind of complacency could easily happen here with some of these other things. Now, I'd say on the other side of it, everybody assumed, because you know, it's very hard to build a database kernel and to do it well. To build one that scales, that offers levels of, you know, ACID compliance. I mean, seriously, look at the network usage of a lot of these NoSQL databases that do things like set gets instead of SQL. And they're sending JavaScript object notation or XML or other stuff basically as text. The chattiness of their protocols is an order of magnitude higher than the worst of the relational databases and their network connections between client and the database. And their ability to store pretty efficiently on disk data is something databases do really well. And the efficiency and the parallelism inherent in database kernels is something, you know, pretty impressive. But they got a little bit, I would say, complacent around that being the only possible way to do things. And now that we relax consistency constraints, in particular around transaction processing because of the internet, we start to look at a whole new realm of possibilities and technologies and architectures all converging at a point when the vendors are too beholden to their cash cows. I mean, Oracle is still not a true MPP database. It's a shared disk structure, and Exadata, while doing a lot to improve I/O efficiency, doesn't really solve a fundamental architectural flaw. Or at least I call it a flaw. They call it a feature.
Here's a really good question, and maybe we can close on this, folks. And by the way, we're going to have 2 more roundtables in this process, and we'll have a findings webcast as well. And when we have our first roundtable, we will launch a survey, so we'll be very curious to get your thoughts on all of that. And, of course, we'll be posting lots of articles and other things at databaserevolution.com. But maybe let's close with this, because I think this is a very interesting and compelling question that one of the attendees asks, saying, do you see a consolidation of some of the different types of databases into a quote-unquote single database, or databases beginning to focus solely in specific areas like we have today? In other words, is there some chance that an Oracle or an IBM or one of these guys could build sort of an overarching service layer on top of many different database types that would have an optimizer that would determine workload and use case and different things of that nature, and then apply the appropriate database technology as needed?
Wouldn't that be nice? I think it's a great vision, but we're a long way from that, from any kind of dynamic provisioning of that sort. But there are already rules of thumb you could use to choose those things, but they're gated by so many factors, including developer skill and languages chosen. What do you think, Robin?
Well, and this whole comment about Oracle buying Sun, I really was stunned by that. I thought that was very odd. Someone I talked to said that their theory was that Oracle was really trying to punch Microsoft in the gut by taking away a bunch of Microsoft of their SQL database, SQL Server database revenue. But there are lots of reasons. I mean, of course, they all, Sun also built Solaris servers, right? So there were a lot of different things going on. But do you have any thoughts on how that all came down the pike? And, I just keep looking at all of these open source projects, and it just seems like they're creeping in from every angle, like the stuff that LinkedIn is doing, and, of course, Facebook and Twitter. And a lot of these guys are doing some very, very interesting things, leveraging a tremendous foundation of open source technology. I guess long term, does IBM have to be concerned about open source database technology? Is it someday going to start peeling away business from DB2, and the same for Oracle?
Good question. I think that's a $1 million question. If we knew the answer to that, we'd be making bets already. But it's definitely a threat. I think, almost all of these databases that have come out are open source, at least to start, and they're ending up at the Apache incubator, or they're ending up somewhere. But most of them, in order to, the problem isn't just technology. If you have smart developers and developer resources available and so forth, you can afford to do a lot more and make things fit. Like I just talked to somebody who said, we really like Cassandra for the website, but we needed to get data out of it and do other things with it. So we rolled our own, basically, for the read optimized side of that. And making this kind of stuff fit inside an enterprise that's, still on 10-year-old software architectures. I'm talking about, the actual architecture of an application, as opposed to a much more modern website, distributed, loosely coupled kind of an architecture. It's going to be a while before that stuff really gets there. So the threat is long-term, but the challenge is getting the legacy to shift off of that and make architectural and technology choices along the way to get there. And you can't really change DB2 to make it suddenly a horizontally scalable, consistency relaxed, highly available across multiple data centers database. I would say possibly you can't do it at all, but and they'll counter me, of course, after this call with DB2 EEE will solve that problem, which it won't. And so, I like the idea of some sort of a virtualized layer that sits above things, but that virtualized layer is probably the services that are exposed by each type of data platform. And then, of course, you have to think, if you're the IT manager, the CIO, whoever, you have to think, I now have a problem of data silos that is worse than the problem that we have ever had before. because it used to all be data silos in relational databases,
right.
mostly. And now it's data silos in things where the only person who can get it out is some guy who knows how to write a Scala or Erlang program and knows the schema or the serialization format of what was put into that thing. So, you know, there's a lot of fundamental technologies to be built around it, and those things are not the kinds of things that developers necessarily enjoy working on. And so that's why open source projects so often have rough edges, which make them hard to adopt by conventional IT, which gates the adoption speed, which gives the big vendors time to figure out how they're going to cope with them.
Right.
Well, that was a long-winded answer.
That was a good answer, though. That's a very good point. Well, folks, I think we'll go ahead and wrap this up. I tried to get to all these questions. My apologies if I didn't get to yours, but like I say, we will have 2 more roundtables. We're very curious to get your thoughts on this stuff. Please send me an email or go to databaserevolution.com. We'll be posting some articles. We'll post an archive of this webcast up there as well. And please send us your questions. Send us your comments. We got a lot of great feedback from our first report last year on the information-oriented architecture, and that really helped us shape and refine the model. So we're very curious to get your thoughts on all that. But once again, folks, thank you very much for all of your time and attention, and I'd be remiss if I did not give a big shout-out to all of our sponsors. Once again, Teradata, Sybase, which of course now is an SAP company, DataStax, MarkLogic, InfoBright, and RainStore. All of these are very interesting vendors. They all have unique advantages that you should certainly check out. So with that, we're going to close up shop, folks. But thank you again for all of your time and attention, and we'll catch up to you next time. Until then, we hope to see you maybe on DM Radio tomorrow. We're going to be talking all about RAM, the power of random access memory. So that's it, folks. Bye-bye.